Yeah. So I will start by describing some very basic property of category of sets that we want to generalize to arbitrary topoi, but we don't know what topoi is yet, so we just want a category to have some good properties, which make this category much like the category of sets. Okay, so first of all, I will start from characteristic functions of subobjects. So obviously, in the category of sets, any subset can be characterized by its characteristic functions, which takes values 0 and 1. And we obtain this subset as a preimage of 1. So in a similar way, we want to do something like that in any other category. So we formalize it like this. Assume that we have a subobject. We want a function phi s from x to set 0, 1, or something like that. We will make it precise later, such that we have the following pullback square. So that's what we have in category of sets. If x and s are a pair of consisting of a set and a subset, then we have a characteristic function phi s, which takes value 1 on points from S and value 0 on points outside of S. And so this intuition leads to the following definition. Let C calligraphic be a category. Subobject classifier C is a monomorphism of the following form. So we have one which is just the terminal object of this category, and we have omega, which in an arbitrary category is a substitute of this set consisting only of 0 and 1. And so this monomorphism should satisfy the following property, such that for any S and X in C, C1. So for any monomorphism in C1, we have pullback square, which looks like this. So we should have the following pullback square, meaning that there is this universal monomorphism which pulls back to any other monomorphism in a category. So assuming that the category, okay, so let me give another definition, more logical in nature. Category that could be well powered if for any object X in C, its subobject form small set. So the word small here means that we just have some regular set, that it's not a proper class. The word small means that basically we use this technology with inaccessible cardinal that says that if something is strictly smaller than this cardinal, it's a small set, and so on. But I won't dive into much details. The thing is that we need this definition to say that we have a functor from category COP to sets, which maps an object to its set of subobjects. So subobjects are monomorphisms into X up to equivalence. So those guys are just monomorphisms to X up to the following equivalence. Okay, so then the condition that we have a subobject classifier is just equivalent to the following. So category C as a subobject classifier if the functor sub C maps, well, not of X, but just of any object is representable by omega. Okay, so now I will formulate a proposition which says precisely this thing, but more rigorously. Finite limits and small concepts. Then he has an object fire. Yeah, so it has a subobject classifier if and only if there is a natural transformation, natural equivalence rejection natural X, which is basically a natural equivalence of factors. Under the latter assumption, it is clear that the category should be well powered, since we assume that home sets are small, thus the set of subobjects should be also small. So, yeah. So let's prove this statement. We start in one direction. If we have subobject classifier 1 to omega. Then there is characteristic function such that for each object S, for each subobject, S is obtained as a pullback along this characteristic function. So this construction of characteristic function gives us a bijection between classes of equivalence of subobjects and functions. So we have a bijection. Okay, so we need to check that this bijection is functorial in X. For this, we will show that for any map F from Y to X, precomposition is F for subobjects corresponds to recomposition in the home set. So this follows from the diagram which I will draw below. So we have two pullback squares placed side by side. And so from the fact that both are pullback squares, it follows that the whole rectangle like this is actually, actually should be a pullback square. So, yeah, so you get the idea. So these four guys form pullback square. And so we obviously have a precomposition in the bottom row, which leads to the fact that actually the notion of precomposition on home set and on subobjects coincide. Okay. Now we prove this fact in the opposite direction. So we prove naturality in X for this theta X. And now we will prove the converse statement that if we have such theta, then we actually have a subobject classifier. To assume that we have such a bijection, which is natural in X, then we want to construct a subobject classifier. So how do we do this? Well, first of all, note that we have an isomorphism of functors. So we have a functor from CO2 sets, and this functor is isomorphic to representable functor also from CO2 sets given by this. Thus, there is subobject omega 0 inside of omega such that theta of omega 0 is equal to identity on omega. So it's basically the standard Ioannidis-Lamé trick. We just look at what is corresponding to the identity morphism, and then we pull it back. Okay, so if we have such a subobject, then we know that any subobject of X corresponds to phi from X to omega. And since theta is functorial, we have the following diagram. Write it down. We have following diagram. So subobjects of omega are isomorphic to morphisms from omega to omega. Here we have a map induced by phi. And here we have an equivalence once again. And here we just have phi, better still phi star. So here we have phi 1. And so at the level of objects, this equivalence amounts to the following. So we have omega 0 here. It maps to identity on omega here. Then it maps to then it maps to phi here, and in the other direction we have S here, and it also maps to phi here. And so what we actually have from this diagram is that S is equal to subobjects to the functor of subobjects applied to phi. So this is another notation for just functor of subobjects applied to phi. This notation is justified because subobjects applied to phi is just precisely the pullback of subobject along certain morphism. And so what we have is that S is obtained from omega 0 by pulling back along phi or by applying this morphism. And so thus any subobject of X is obtained as a pullback of omega 0. So potentially we already got our classifying map, our subobject classifier, which is just an inclusion from omega naught to omega. And we also got our map, which pulls everything back. So this characteristic function. But we actually need to check that this for each subobject, this phi is unique. That's what we will do now. So we need to, not only to check that phi is unique, but also to check that, in fact, this thing should be the terminal object in the category. And we need to check that, and we will do it in just a moment. Okay, so how we will do this? First of all, consider an inclusion of X into itself. It corresponds to certain phi prime from X to omega naught. If we had two different possible maps, not just phi, but also phi prime, if phi prime is not unique, then since T naught from omega 0, omega naught to omega is a monomorphism, we have the following. We have X to X, which is just the identity. Omega 0 to omega, which is just T0. And here we have T0 phi prime. And we also have another square of the similar nature, but for the other map. So perhaps we had phi prime and phi 2 prime. Then what we get here is the same square, but here we get T0 phi 2 primes. But since actually we have a pullback square, it implies that, well, that actually these two things here are the same. So T0 phi prime should be equal to T0 phi 2 primes. And since T0 is monic, we can just cancel it out. And we get that phi prime is equal to phi 2 primes, which means that we actually have a unique map. Prime is a unique map from any object to omega naught. Thus, omega naught is precisely the terminal object. So yeah, we've proven that omega naught is terminal, and we've proven that by explaining why from each object we have one and only one map to it. So that's precisely the universal property of terminal object. Okay. So basically, the idea of subobject classifier is inspired by topology, and I will just give a probably familiar topological example of how this thing works. So assume, for example, that we have a functor G band of X, which just corresponds to G fibrations over X up to equivalence. So they are classified by maps from X to BG to EG. So EG should be universal bundle, BG should be classifying space. And so we obtain any E from this set from a pullback of this universal bundle. For example, so yeah, and that's the very same picture that we have here. So here we just pulled back the universal monomorphism, and here we pull back the universal bundle. So the idea is the same, and yeah, that's the reason basically behind all this stuff, that we can represent subobjects by some universal subobject. Yeah, okay. So that was somewhat of a topological motivation for this concept. And now I want to turn to sort of applications of subobject classifiers in real life. Of course, by real life, I mean some familiar categories, but nevertheless, let's examine it. So, subobject classifiers. Okay, so example number 1 are finite sets. And here we have the same subobject classifier as in ordinary sets. So finite sets, and here we have just a map which maps 1 to 1 in so this thing lives in the set consisting of 2 possible values, 0 and 1. So less trivial example is provided by, well, it's also pretty trivial, but somewhat less trivial. We can take a product of 2 copies of category of sets, then a map from a pair is just a pair of maps. So this thing here gives us an arrow like this. And hence, classifier subobjects just I'm sorry, I seem to have small technical difficulty. Will take a moment. Sorry, I will pause the recording here. That I managed to overcome the issue. Okay, so the classifier of subobjects inside of set times set is just a map from a pair 1 times 1 into 2 times 2. And so in general, the same thing works. So 1 times 1 consists just of 1. And it is mapped, sorry, it is mapped to 1 times 1 here. Yeah, and so the same thing works, of course, for product of n copies of the category of sets. Okay, so another example is provided by the category of G sets. So G sets are just actions of G from the right, for example, on X. So a subobject is just a G invariant subset. Since yeah, so G invariant subset S, since X without S is also G invariant, the ordinary characteristic function will do the job of classifying subobjects. Sorry. I'm sorry, I have still have some technical difficulties. Maybe one more moment. Okay. 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 Okay, so the ordinary characteristic function will do the job of classifying subobjects because its values, because both its domain and the complement of its domain are G invariant. Therefore, the function itself is G equivariant. Really bad. So sorry. Okay, so the function is G equivariant, therefore it satisfies the property of subobject classifier. The same thing can be said about monoids. So the same thing can be said about monoids. So if we consider M a monoid, then we can say that the complement of an invariant subset is necessarily invariant itself. For example, does not imply that X without S is an invariant. An example of this is given for instance, by nilpotent operators. So if A is nilpotent, acting on a vector space, then V without zero is not invariant. However, we can somewhat fix it by considering the following construction. Yeah, okay, so in view of the technical difficulties, I think I will make a break here for like 5 minutes and I will try to fix them. And if this will work, we will continue. Yeah, we will continue in 5 minutes. I'm deeply sorry, but I am not ready to explain this example with my tablet working as bad as it is now. I'm sorry once again. Fix the problems. So yeah, as I was saying, we have a monoid, we have M sets with M action, and we have a subset S inside of X, which is M invariant. M invariant subset. So we know that its complement is not necessarily invariant. And as I explained, we can consider a nilpotent operator acting on vector space, and so zero is invariant, and V without zero is not invariant because this monoid eventually maps all of this complement inside of zero. Okay. However, we can fix this construction and define the characteristic function in the following way. So let's map a point inside of X capital into L, which is defined like this. Those are precisely those L small inside of M, such that X times L belongs to S. So that's basically an ideal of inside of a monoid, which consists of those elements which map our fixed point into S. So L is a right ideal in M. Assume that omega is by definition, or omega M, set of all right ideals in M. So we have an action of M on this omega M via the following formula, sorry. So L dot M is mapped to K and M such that MK belongs to L. So that's an action. So we see that omega M is in fact an M set. Okay. Now we define the characteristic function. The characteristic function looks like this. So it just maps each point of X into the following ideal. So well, let me just copy it real quick. Okay, so that's our characteristic function. And now what we want to do is we want to explain how we get back the set S, and we do this just by taking the pullback of the maximal right ideal of M itself. So yeah, that's precisely S. So we get the classifier, this one is just consisting of one. It's a one object set with trivial M action. So one object set, trivial action, and it is mapped to maximal ideal here. Note that if M is actually a group, then the set of all right ideals consists only of two, 0 and 1, where 0 is an empty idea, sorry, not empty. No, not empty ideal consisting of just yeah, I think of empty ideal and of the whole M. Yeah. So that shows that this example is a generalization of the previous example for groups. Okay, so now we move on to functor categories. We will talk a lot about functor categories today. So another example is the following. So we can consider a category of sets of functors from two-element category to sets. And well, a two-element category is like Kronecker quiver, so it's just 2 points and an arrow between them. That's what I mean by two-element category. And so a subobject is precisely the following thing. So we have this diagram consisting of two objects. We have a diagram consisting of another two objects. And so we should have monomorphisms here and, well, inclusions, because we work in sets, so just inclusions here and here. And also we should note that these inclusions should be equivariant with respect to sigma. So sigma of S0 should be inside of S1. Okay, so now we can split the set X0 into three parts. We have the three distinct possibilities. So X small already belongs to S0. X small does not belong to S0, but sigma of X belongs to S0. Finally, X does not belong to S0, and sigma of X does not belong to S1 either. We may now define the characteristic function like this: phi 0 X is 0, 1, or 2 for the respective cases. So we have three cases here. And we take the values which correspond to those cases. Okay, and so we can now form a pair consisting of phi 0 and phi 1. Phi 0 is defined above. and phi1 is just an ordinary characteristic function of S1 in X1. Then what we get here is precisely the following diagram. So we have X0 goes to X1 by sigma. We have phi 0 goes to 0, 1, 2. We have the set 0, 1. We have phi 1. And here we have sigma tilde, which works like this. Sigma tilde of 0 is equal to sigma tilde of 1 is equal to 0. And sigma tilde of 2 is equal to 1. We now obtain S equal to S0 to S1. As a pre-image of zero to zero, and which goes to omega. So this guy here is obviously omega. Under phi 0, phi 1. So this construction may seem complicated at first glance, but the basic idea behind it is quite simple. So the characteristic function can be thought of as follows. We have three distinct possibilities. So an element is already inside of the subobject S. An element gets inside of S after we pass one arrow or after one tick of time. And an element does not get inside of S ever. So that's the basic idea of characteristic function. And that's how we classify these subobjects. So we just need to know after how many arrows an element gets inside of this subobject. And so the similar construction works for a category which is a representation of the following infinite chain. And you just say that we have a characteristic function which is valued in the set of from 0 to infinity, and it measures after how many steps our element gets inside of the subobject. So that's an idea behind the classifying function for such functor categories. But we now move on to general context of pre-shift categories. So we had this just very tame functor categories from, for example, two-element set or natural numbers. But now we will just consider arbitrary functor categories. So category of pre-shifts. Okay. So definition number 4 is the following. So a subfunctor from 0 to set is the functor Q from also from 0 to set, such that for any C, for any object C capital, we have Q of C capital is a subset of P of C capital, and QF for any morphism from QD to QC. I'm sorry, from QD to QC. So if we have a morphism inside of C from D to, better still, in C op from D to C. So this morphism here is obtained as a restriction of P of F. QD. Okay, so that's the definition of subfunctor. Now we want to investigate subobjects inside of arbitrary functor from C op to set. So first of all, we note that subobjects in this category are precisely subfunctors. Now, yeah, so to note this, we just have to consider a natural transformation, which is a monomorphism from R to P. Then it means that since monomorphisms are computed object-wise, we have that RC is an inclusion for each object. And so we can say that Q corresponding to this monomorphism theta C, to this monomorphism theta, is just an image. QC is just an image of theta C. Okay, and so Q then evidently becomes a subfunctor of P. So that is not a, I mean, it's almost a triviality what I've just said. Now, to understand how the subobject classifier works for arbitrary presheaf categories, it is sufficient to look at how it works on representable presheaves. So let us do this. So consider a subobject classifier representable presheaves. So that's just a unary embedding of an object C. Works from C op to set. And so what we get for subobjects, those are just subfunctors as we expect them to be. But also they're maps from this representable functor to this subobject classifier. Now by Unida lemma, we have that this thing here is in fact isomorphic to omega of C. Okay. And so omega is given as a presheaf AK on objects as omega of C should be equal to subobjects of inside of presheafs of this functor. Well, this description is not very satisfactory, of course, but we will obtain a more satisfactory description by the end of the talk. Okay, so that's basically the description of subobject classifier in some sense. But we can do better. And to do this, we need to consider sieves. So that's a small, tiny bit of Grothendieck topology, without the words Grothendieck topology, of course, which help us to construct subobject classifiers inside of presheaf categories. Okay, so let me explain what a sieve is. So, sieves. Okay. So first of all, let C be an object inside of C curly. And so a sieve on C, the collection of morphisms such that for any F inside of S and H, a morphism from X to the domain of F, we have FH also belongs to S. So this can be represented by the following picture. So we have some holes inside of the sieve. And we have a morphism F, which goes through one of the holes. That means that everything that can be added to this morphism, for example, any morphism of this form, also goes through the hole. So we can introduce a partial ordering on morphisms and say that a morphism is greater than other morphism if one can be obtained as a composition of the greater one and some another morphism. And so that's basically an ordering by length, sort of. And then this is made precise because we say that everything that if something goes through the sieve, then everything smaller also goes through the sieve. So that's the basic reasoning behind the name sieve here. Okay. So yeah, and another way to think about it is that a sieve is just a right ideal an arrow category over C. And this can be made precise in the case of monoids. So what is an ideal inside of a category is somewhat esoteric, but for monoids, it's very simple because we just have one object. And so sieve is precisely the right ideal on a monoid, of a monoid. So in particular, So in particular, on a monoid, this is precisely a right ideal. Okay, so now how is it related to subfunctors? Assume that we have a subfunctor Q inside of the functor of homomorphisms subfunctor. Then S such that for some A. So yeah, for some A and A from A to C, F belongs to Q of A. Oh, wait a second, something is terribly wrong here. Something is so terribly wrong here. Wait a moment. Yeah, so for some object A, yeah. Yeah, so this thing here consists of such morphisms that wait a moment. I don't quite understand. Oh no, it's fine because yeah, Q is a subfunctor inside of yeah. It's okay. So Q is a subfunctor inside this home functor, and so Q of A is precisely a certain distinguished subclass of morphisms, and so it defines the sieve on C. Yeah, so that's the construction. Yeah, right. Okay, so this is a sieve corresponding to subfunctor Q, and we can construct an inverse. Well, we can construct an inverse procedure. We can obtain from a sieve a subfunctor, and we do it like this. Let us be sieve C. Then Q of A consists of those F from A to C, such that F belongs to S. So that's basically tautological, that we just subfunctor is taking certain morphisms from this set here, and the sieve also takes certain morphisms from this set here. So basically that is tautological, that we have the following equivalence. So sieves C are equivalent to subfunctors Of course, for everything to work here, we must assume that the category C is small, otherwise it is not clear why, for example, all morphisms that go into fixed object form a set and not a class. But we can make such an assumption, so here C is small. Okay, so we have such an equivalence, and now we can also observe that this equivalence is natural in C, meaning that if we have a morphism, so G from B to C be a morphism. Then we can take a subfunctor inside of this home functor, and we can pull it back along G to obtain a subfunctor inside of home C B. How do we do this? Well, we just say that basically subfunctor is so we have certain morphisms. So for any object A, we have Q of A, which is just a subset of home A to C. And we can just take all morphisms. So we take home from A to B. We have a morphism here. And we define a subfunctor as a pre-image of Q of A here. So I think that this is even a better notation. So G minus 1 of Q of A here. Okay, and so we can do the similar thing for sieves. If S is a sieve on C, then we have a sieve G minus 1 S on B defined like this. So that's precisely the pre-image of the sieve on B. And so we obtained the following equivalent description of the classifier of subobjects on, well, of the value of this classifier, if it even exists, on an object C. So it consists precisely of those S which are sieves on C in C curly. And the value on arrows of this omega is also clear because we just described this inverse image of sieves. So omega is defined as recomposition like this. So an action of morphism G on S is just H such that GH onto S. Okay, now to construct a universal subobject classifier, not just a value on C, we need the following thing. So we have a maximal sieve for each object. For each object C, said C earlier. We have a maximal sieve, which is denoted by T of C. The notation is explained by the fact that later we will see that those are in some sense truth values. So T for truth. So this is just a set. Recall that our category is small. set of all arrows going to C. So we can glue those maximal sieves to get a natural transformation from 1 to omega. So it just takes the terminal object and it maps it for each object C to the maximal sieve on this object. So 1 on C is still 1, and we map this 1 or 1 point set to the maximal sieve T of C inside of omega C. So we constructed the following pair, and we will now see that it is in fact a subobject classifier. Okay, so let Q be a subfunctor P from the opposite to set. Then bring F from A to C. In C curly, we have a function so it was an opposite category, so from PC to PA. So this function is characterized by the following property. It either maps a fixed element X, is either mapped Q of A inside of Q of A or not. So based on this, we can construct a characteristic function P C of X consisting of F from something to C, such that composition of X and F, well, we denote by this an action of F on X, but that's just a composition, belongs to Q of this question mark. Then what we have defined here is a sieve. Is a sieve on C, and phi is a natural transformation from P to omega. Yeah, because it just takes an object and it creates a sieve based on it, and it maps this sieve to, so it maps each functor to this distinguished sieve that we obtained from knowing the subfunctor Q. Okay. Moreover, we know that on value of phi c x, phi c on x is this maximal sieve, precisely if and only if X already belongs to Q of C. So just looking at this definition, we see that basically any arrow fits the description if and only if X is already inside of Q of C. And so what we get is the following commutative diagram. Let's denote star. And so phi is indeed a possible characteristic map. We also need to show that phi is in fact a unique natural transformation. So is a unique natural transformation from P to omega such that this star diagram becomes a pullback. Okay, so to see this, we just need to observe that for this diagram to be a pullback, it is necessary that the following equivalences hold. So XF belongs to Q of A, if and only if theta A of XF. So theta is now something that lives here. And by naturality of theta, natural, we have the following. So we can just pull F outside of the brackets. And so this in turn is equivalent to F belonging to theta C of X. Thus, F inside of theta C of X are precisely those that satisfy the following. So XF belongs to Q of A, which is in turn equivalent to F belonging to phi C of X. Thus, we've just explained why phi C is uniquely determined by the condition that the starry diagram is a pullback. And so this shows, in fact, that 1 to omega given by this true function is, in fact, a subobject classifier of this category. So one way to, so we've shown that we have a subobject classifier for arbitrary pre-shift category. We constructed it. And so a way to think about it is that actually this phi c of x set of paths or morphisms f c such that xf is in Q. So this is very similar to this two-element category. However, now we have this whole plethora of different possible arrows we can go and different roads we can go. And so the characteristic function once again determines when we get to Q. Maybe we get to Q after one arrow, maybe we get to Q after two arrows, maybe we get to Q after some very elaborate combination of arrows. But the basic idea is the same as with two-point set with one arrow. So so that's the previous example with two-point category was just an illustration of this general principle that I tried to show here. So I think I will stop here for today. I'm sorry, I'm afraid that the first half of the notes got erased after this technical debacle, but hopefully I can restore some of the notes from the video that remains, and I will, I will publish the whole notes. Okay, thank you for coming.